So here's something I want you to think about as you settle in tonight. You've probably heard the word torque before. Maybe someone used it when talking about a car engine or a wrench, or maybe you saw it on a spec sheet somewhere and just kind of glossed over it. And that's fine. But torque is one of those concepts that, once you really understand it, starts showing up everywhere. It's in the way you open a door. It's in the way a helicopter stays in the air. It's in the reason your car can climb a hill. And the story of how humans figured it out, how we went from not even having a word for it to building machines that depend on it with absolute precision. That story is genuinely fascinating. So let's just talk about it. No rush. Let's see where it goes. Let's start with something simple. Imagine you're trying to open a really heavy door. Not a regular door. One of those thick, old wooden doors you might find on a cathedral or an old courthouse. Now, if you push on that, daughter right next to the hinges, almost nothing happens. You can push pretty hard and the door barely moves. But if you push on the far edge, way out at the handle, the door swings open easily. Same door, same you, same amount of effort even. But the result is completely different. And the reason is torque. Torque is just a twisting force. That's it. It's what happens when a force tries to rotate something around a point. The key insight, and this is the part that took humanity a surprisingly long time to formalize, is that torque depends on two things: how hard you push and how far from the pivot point you push. Multiply those two together and you get torque. Push harder, more torque. Push farther from the pivot, more torque. That's why door handles are on the opposite side from the hinges. That's why long wrenches make it easier to loosen a stubborn bolt. You're not adding more force, you're adding more distance, and distance is a multiplier. Now, that might sound obvious when I say it out loud, but think about what that means. It means that a small person with a long enough lever can generate more turning force than a large person with a short one. It means that the geometry of a situation, the shape, the layout, the distances involved, matters just as much as raw strength. And that idea, that geometry can amplify force, is one of the oldest and most powerful ideas in all of engineering. The person who probably understood this best, at least in the ancient world, was Archimedes. You've heard of him. He's the guy famous for running naked through the streets of Syracuse shouting "Eureka" after figuring out how to measure the volume of irregular objects in a bathtub. Great story, probably embellished, but the man himself was very real. He lived in Syracuse, on the island of Sicily, around 287 to 212 BC, and he was arguably the greatest engineer and mathematician of the ancient world. Archimedes is the one who reportedly said, "Give me a lever long enough and a fulcrum on which to place it, and I shall move the world." And he wasn't being poetic. He was being literal. He understood, mathematically, that a lever is a torque machine. The fulcrum is the pivot point. The longer the lever arm on your side, the more torque you generate, and the heavier the thing you can lift on the other side. He worked out the law of the lever, that a system is in balance when the force on one side times its distance from the fulcrum equals the force on the other side times its distance. It's elegant, it's simple, and it governs everything from seesaws to scissors to the way your own jaw works when you chew food. But here's the thing about Archimedes. He didn't just theorize about this stuff. He built machines. During the Roman siege of Syracuse in 214 BC, Archimedes designed war machines that held off the Roman fleet for nearly 2 years. He built cranes that could reach over the city walls, grab Roman ships, and flip them. Imagine that. You're a Roman soldier, You've sailed across the Mediterranean, you're approaching the walls of this city, and suddenly a giant mechanical arm reaches out, hooks your ship, lifts the bow out of the water, and dumps you into the sea. The Roman general Marcellus reportedly said that Archimedes was like a mythological, hundred-handed giant, the way his machines kept swatting away the fleet. And those machines were torque machines, every one of them. The cranes used long lever arms to multiply the force of the soldiers operating them. The catapults stored energy and released it through rotating arms. Archimedes understood, intuitively and mathematically, that rotational force could be harnessed, amplified, and directed. He didn't use the word torque. That word comes from the Latin torquere, meaning to twist, and it wouldn't be used in its modern engineering sense for many centuries. But the concept was there. The physics was there. Now, let me take a little detour here, because I think it's worth understanding why torque is confusing to people in the first place. And I think the confusion comes from the fact that we learn about force first. Just plain, straight-line force. And then, torque comes along and adds a twist. Literally, when you push something in a straight line, the physics is pretty intuitive. Push harder, it accelerates more. Heavier object, harder to accelerate. That's Newton's second law. Force equals mass times acceleration, and most people have a gut feel for it, even if they've never written the equation. But torque adds a new dimension. It's not just about pushing. It's about where you push and in what direction relative to the pivot. And instead of mass, you have something called moment of inertia, which is how the mass is distributed around the axis of rotation. And this is where people's eyes start to glaze over. So let me give you an analogy. Think about an ice skater doing a spin. When the skater pulls their arms in, close to their body, they spin faster. When they extend their arms out, they slow down. Same person, same amount of rotational energy, but the speed changes. Why? Because moment of inertia changed. When the mass, their arms, is farther from the axis of rotation, the moment of inertia is higher, and it takes more torque to spin them at the same speed. Pull the mass in closer, moment of inertia drops, and they speed up. This is conservation of angular momentum, and it's beautiful. It's the same reason a figure skater can go from a lazy, graceful spin to a blur just by tucking their arms. And this connects back to torque, because torque is what creates and changes rotational motion. Torque is to rotation what force is to straight-line motion. If force makes things go in a line, torque makes things spin. And just like force, torque can be in balance, which means something can be spinning at a constant rate without speeding up or slowing down. Or it can be out of balance, which means the rotation is accelerating or decelerating. Now, here's where this gets practical. Think about a car engine. Inside that engine, pistons are moving up and down. That's linear motion, straight line, back and forth. But your wheels need to rotate. So somehow the engine has to convert that up and down motion into spinning motion. And it does this with a crankshaft. The crankshaft is basically a cleverly shaped rod that the pistons push on, and because of the geometry, because the point where the piston connects to the crankshaft is offset from the center of rotation, that push creates torque. The crankshaft spins, and that spin eventually makes it to your wheels through the transmission and the drivetrain. When car people talk about an engine producing, say, 300 foot-pounds of torque, they're describing a specific amount of twisting force. 1 foot-pound means that if you had a wrench 1 foot long, the force at the end of that wrench would be 1 pound. 300 Foot-pounds means the engine is generating enough twisting force that, if you attached a 1-foot lever to the crankshaft, you'd feel 300 pounds of force at the tip. That's a lot. That's enough to seriously accelerate a 2-ton vehicle. And here's something that trips people up. Torque and horsepower are not the same thing, even though they're related. Torque is the twisting force at any given moment. Horsepower is torque multiplied by how fast the engine is spinning, so you can have a lot of torque at low speed. Think of a big diesel truck engine that can pull enormous loads from a standstill. Or you can have less torque but at very high speed, which gives you high horsepower. A Formula One engine makes its power by spinning incredibly fast, sometimes over 15,000 revolutions per minute. A big tractor engine makes its power by generating massive torque at much lower speeds, maybe 2,000 revolutions per minute. Different strategies, same underlying physics. This distinction between torque and power, between the instantaneous twist and the rate at which that twist does work over time, took engineers a long time to sort out clearly. James Watt, the Scottish inventor who improved the steam engine in the 1760s and 1770s, was one of the first to really grapple with this. He needed a way to tell potential customers how much work his steam engines could do, so he compared them to horses. He watched horses pulling loads at a coal mine, estimated that a strong horse could do about 33,000 foot-pounds of work per minute, and called that one horsepower. It was a marketing move as much as a scientific one, but it stuck. And it gave the world a unit that connected force, distance, and time in a way that made the concept of power concrete and comparable. What Watt was really doing, even if he didn't frame it exactly this way, was connecting torque to practical output. His steam engines produced torque. They turned a shaft. And the question was always, how much torque? And how fast? Because a shaft turning slowly with enormous torque and a shaft turning quickly with modest torque can do the same total amount of work per minute. They just do it differently. And which one you want depends entirely on the job. If you're lifting heavy ore out of a mine, you want high torque. If you're spinning a textile loom at high speed, you want the RPMs. This is why gears exist, by the way. Gears are torque converters. A small gear driving a large gear trades speed for torque. The output turns slower, but with more twisting force. A large gear driving a small gear does the opposite. More speed, less torque. And this is exactly what happens in your car's transmission. When you're in first gear, the engine's torque is being multiplied through the gear ratio so you can accelerate from a stop. When you're in fifth or sixth gear on the highway, the gear ratio is trading torque for speed because you don't need as much force to maintain your cruising velocity. You just need the wheels turning fast. Gears are ancient, by the way. The Antikythera mechanism, that astonishing Greek device found in a shipwreck off the coast of a small island between Crete and the Peloponnese, dates to around 100 BC, and it's full of precision bronze gears. It was an astronomical calculator, a mechanical computer of sorts, and its gear trains converted rotational motion from one rate to another so that different dials could track the sun, the moon, and the planets at their different speeds. The craftsmanship is almost unbelievable for the era. When it was first X-rayed in the 1970s and researchers saw the interlocking gear teeth inside, some of them genuinely couldn't believe what they were looking at. It was like finding a Swiss watch in a Roman tomb. But what the Antikythera mechanism really demonstrates is that ancient engineers understood gear ratios, which means they understood, at least practically, the relationship between torque and rotational speed. They knew that meshing gears of different sizes changed the behavior of the output. They might not have written equations about it, but they could build it, which in some ways is even more impressive. Now there's another concept tangled up with torque that I want to start unwinding, because it confuses almost everyone the first time they encounter it. And that's the idea of a moment. In engineering, a moment is essentially the same thing as torque. It's a force times a distance from a pivot point. But the word moment tends to show up more in structural engineering when people are talking about beams and bridges and buildings, while torque shows up more in mechanical engineering when people are talking about shafts and engines and rotating things. Same math, same physics, different context. And the reason this matters is that every beam in every building you've ever been in is dealing with moments right now. The beam is trying not to bend, and bending is a rotational phenomenon. One part of the beam is trying to rotate relative to another part. The moment is what's causing that, and the beam's strength and shape are what's resisting it. Think about a diving board. When a diver stands at the end, the board bends downward. The weight of the diver, multiplied by the distance from the fixed end of the board, creates a moment, a bending moment, at the attachment point. The farther out the diver stands, the bigger the moment, and the more the board bends. If the diver is too heavy, or the board is too long, or the material is too weak, the board snaps. And it snaps at the point of maximum moment, which is right where the board meets the platform. That's why diving boards are thickest at the base and taper toward the tip. The designers are putting the most material where the moment is greatest. And this same logic governs every bridge, every floor joist, every airplane wing, every crane boom. Engineers calculate the moments at every point along a structure, figure out where the bending forces are greatest, and make sure the structure is strong enough at those points. It's one of the most fundamental things in structural engineering, and it all comes back to that same simple idea. Force times distance from the pivot, torque, moment. The twisting, bending, rotating tendency that force creates when it acts at a distance. So we've got this concept, torque, and we've seen it in levers, in engines, in gears, in beams, and we've traced it back to Archimedes at least. But the story of how engineers learned to really calculate and predict torque, to make it precise enough to design safe structures and efficient machines, that story takes us forward in time, to the Renaissance and beyond, to a period when people started getting serious about the mathematics of how things actually work. And the person who really kicked that off, at least when it comes to understanding how beams bend and structures carry load, was a man you've probably heard of for completely different reasons. Leonardo da Vinci. Now, Leonardo is famous for his paintings, obviously. The Mona Lisa, The Last Supper. But if you dig into his notebooks, and there are thousands of pages of them, filled with these beautiful mirror-written notes and sketches, you find someone who was absolutely obsessed with mechanics. He studied pulleys, levers, gears, friction, the flight of birds, the flow of water. And one of the things he kept coming back to was the strength of beams. He wanted to know, if you have a wooden beam supported at both ends and you hang a weight from the middle, how much weight can it take before it breaks? And how does that change if you make the beam longer or thicker or use a different kind of wood? Leonardo didn't have calculus. He didn't have the formal mathematical tools that would come later, but he had incredible intuition, and he ran experiments. He tested beams of different lengths and thicknesses, loaded them up, and recorded what happened. And he arrived at some remarkably good insights. He figured out that a beam's resistance to bending depends on its cross-section, specifically that a deeper beam is much stronger than a wider one. If you double the depth of a beam, its resistance to bending goes up dramatically, much more than if you just double the width. He didn't get the exact mathematical relationship right, but he was circling the truth. And the truth, as engineers eventually worked out, is that the resistance to bending depends on the cube of the depth. So if you double the depth of a beam, it becomes 8 times as resistant to bending. That's why floor joists in your house are tall and narrow. They're oriented with their depth running vertically, because that's where you get the most bending resistance for the least amount of material. Leonardo sensed this. He couldn't prove it rigorously, but he knew it mattered. The person who really started putting this on a rigorous footing was Galileo Galilei. And here's the thing about Galileo. Most people know him for the telescope, for arguing that the Earth goes around the sun, for his conflict with the Catholic Church. But his last major work, published in 1638 while he was under house arrest, was called Two New Sciences, and it's arguably one of the most important engineering texts ever written. One of those two sciences was the study of the strength of materials and structures. Galileo asked a deceptively simple question. Why can't you just scale things up? Why can't you take a small wooden beam that works perfectly well and just make it 10 times bigger and expect it to hold 10 times the load? And his answer was brilliant. He realized that when you scale something up, its weight increases faster than its strength. The weight goes up with the cube of the scaling factor, because weight depends on volume, and volume is length times width times height. But the strength of a cross-section only goes up with the square of the scaling factor, because strength depends on area. So if you double every dimension of a beam, it becomes 8 times heavier, but only 4 times stronger. Triple every dimension, and it's 27 times heavier, but only 9 times stronger. Eventually, if you keep scaling up, the structure collapses under its own weight. This is why you can't have an ant the size of a dog. Its legs would snap. It's why elephants have proportionally much thicker legs than gazelles. And it's why engineers can't just take a design that works at one scale and blindly scale it up. Galileo figured this out in 1638, and it's still one of the most important principles in engineering. Now, Galileo also tackled the specific problem of a cantilever beam, a beam that's fixed at one end and sticking out into space, like a balcony or a flagpole or, yes, a diving board. He analyzed the forces and tried to figure out where and how it would break. And he got the basic setup right. He understood that the bending moment is greatest at the fixed end, that the beam would fracture there first, and that the material on the top of the beam would be stretched, while the material on the bottom would be compressed. But he made an error in his analysis. He assumed that when the beam breaks, the entire cross-section is under tension, being pulled apart uniformly. In reality, part of the cross-section is in tension, and part is in compression, with a neutral axis running through the middle where there's neither. This mistake meant his predictions for breaking strength were off by a factor of about 3. But here's what matters. He set up the problem correctly. He framed it as a problem of moments, forces, times, distances, and he showed that you could, in principle, calculate whether a beam would hold or break. He gave future engineers the framework, even if he didn't fill in every detail correctly. And those details got filled in over the next century or so by a parade of brilliant people. Robert Hooke, the English polymath, discovered in 1660 that materials deform proportionally to the force applied to them, what we now call Hooke's law. Pull on a spring with twice the force, it stretches twice as far. Bend a beam with twice the moment, it deflects twice as much. This linear relationship between force and deformation is the foundation of almost all structural engineering, and it holds true as long as you don't push the material too far. Once you exceed a certain limit, the elastic limit, things get non-linear. The material starts to permanently deform, and eventually it breaks. But within that elastic range, everything is beautifully predictable. And that predictability is what lets engineers design things with confidence. Then came the Swiss mathematician Leonhard Euler and the French engineer Claude-Louis Navier in the 18th and early 19th centuries, who worked out the full mathematical theory of beam bending. Euler, in particular, tackled the problem of buckling. What happens when you push on a slender column from both ends? Think about holding a yardstick vertically and pressing down on the top. At first, nothing happens, and then suddenly it bows out to the side and collapses. That's buckling, and it's a torque problem in disguise. The column doesn't fail because the material is crushed. It fails because a slight sideways bend creates a moment, and that moment causes more bending, which creates a bigger moment, which causes more bending in a runaway feedback loop. Euler worked out the critical load, the exact force at which a column will buckle, and his formula, published in 1757, is still used today. It depends on the column's length, its cross-sectional shape, and the stiffness of the material. And here's a detail that's almost poetic. The resistance to buckling depends on something called the moment of inertia of the cross-section. Same term, same concept as the moment of inertia we talked about earlier with spinning objects. It's a measure of how the material is distributed relative to an axis. A hollow tube has a much higher moment of inertia than a solid rod of the same weight, because the material is spread farther from the center. That's why bicycle frames are made of hollow tubes, not solid rods. Why bamboo is hollow. Why your bones are hollow. Nature and engineers arrived at the same solution independently. Spread the material out from the center to maximize resistance to bending and buckling, while minimizing weight. Navier, meanwhile, pulled together the work of Galileo, Hooke, Euler, and others into a coherent theory of structural analysis. In 1826, he published a textbook that essentially became the Bible of structural engineering for the next half-century. He showed how to calculate stresses and deflections in beams, columns, and frames under any combination of loads. He formalized the idea of the neutral axis, that line through the middle of a bending beam where there's no tension or compression, and showed that the stress in a beam increases linearly as you move away from the neutral axis. The material farthest from the center carries the most stress, which, again, is why I-beams are shaped the way they are. You know those steel beams with the wide flanges on top and bottom, connected by a thin web in the middle? That shape puts most of the material as far as possible from the neutral axis, right where the bending stresses are highest. The thin web in the middle barely contributes to bending resistance. It's mainly there to keep the two flanges connected and to resist shear forces. It's an incredibly efficient shape, and it comes directly from the mathematics of bending moments. Every steel-framed building you've ever been in, every bridge you've driven over, is full of these I-beams, and their shape is a physical embodiment of the math that Navier and his predecessors worked out. So by the mid-1800s, engineers had a pretty solid theoretical toolkit for dealing with torque and moments in structures. They could predict how beams would bend, when columns would buckle, and where the critical stresses would occur. But theory is only as good as its application. and the 19th century was about to test that theory on a scale nobody had attempted before. Because this was the age of iron and steel, the age of railways and long-span bridges, and the consequences of getting the math wrong were about to become terrifyingly clear. Let's talk about one of the most important and heartbreaking engineering failures in history. On the evening of December 28, 1879, a violent storm swept across eastern Scotland. Wind speeds may have reached 90 miles per hour or more, and in the middle of that storm, a passenger train was crossing the Tay Bridge. At the time, the longest bridge in the world, stretching nearly 2 miles across the Firth of Tay near Dundee. The bridge had been open for less than 2 years. Its designer, Thomas Booch, had been knighted for it. It was considered a triumph of Victorian engineering. And then, in the darkness and the howling wind, the central spans of the bridge collapsed into the river, taking the train and all 75 people aboard with it. There were no survivors. The investigation that followed revealed a cascade of problems, and many of them come back to moments and forces that the designer either underestimated or ignored. Bouch had drastically underestimated the wind loading on the bridge. The Board of Trade at the time suggested designing for wind pressures of about 10 pounds per square foot, and Bouch may have used even less than that. Some accounts suggest he barely accounted for wind at all in his original calculations. The tall, slender, cast-iron columns that supported the high girders of the central navigation spans were simply not strong enough to resist the enormous bending moments created by hurricane-force winds pushing against the side of the bridge and the train. The wind created a lateral force, and that force, acting at the height of the bridge deck, high above the base of the columns, generated a massive overturning moment. The columns, the bracing, the connections, none of it was adequate. There were also serious problems with the quality of the cast iron. The foundry had used a technique called burning on to fill blowholes and defects in the castings, essentially patching flawed components rather than recasting them. The bolt holes in the lugs that connected the bracing bars were found to be poorly made, with rough surfaces and inconsistent dimensions. Under the cyclic loading of wind and train vibrations, these connections gradually loosened and weakened. The Tay Bridge disaster was a watershed moment. It forced engineers to take wind loading seriously, to think carefully about dynamic forces, not just the static weight of the structure and its load, but the fluctuating, unpredictable forces of nature. And it reinforced a lesson that engineers keep having to relearn, that a structure is only as strong as its weakest connection. You can have the most beautiful, mathematically perfect design in the world, but if the bolts are loose, if the castings are flawed, if the guy who poured the iron-cut corners, none of that math matters. The bridge that replaced it, the second Tay Bridge, completed in 1887, was massively overbuilt by comparison. Its designer, William Henry Barlow, was determined not to repeat the mistake. And just a few miles to the south, another bridge was rising that would become one of the most iconic structures in the world, designed by engineers who had the Tay disaster seared into their minds. That bridge was the Forth Bridge, and the story of how it was designed and built is one of the great engineering tales of all time, a story where torque, moment, and the lessons of catastrophic failure came together in a structure so bold, so innovative, that people still argue about whether it's beautiful or terrifying. Honestly, it might be both. The Forth Bridge. If you've ever seen a picture of it, you know exactly what I'm talking about. That massive red structure stretching across the Firth of Forth in Scotland, with its 3 enormous diamond-shaped cantilever towers connected by spans that seem almost impossibly long. It doesn't look like any other bridge. It looks like something alive, like some great steel creature crouching over the water. And the reason it looks the way it does, the reason every single piece of it is where it is, comes down to torque, to bending moments, to the very principles we've been talking about. So here's the backstory. After the Tay Bridge collapsed in 1879, there was already a design in progress for a bridge across the Firth of Forth, which is another estuary not far away. The original designer was Thomas Bouch, the same Thomas Bouch who had designed the Tay Bridge. He had proposed a suspension bridge for the Forth crossing, and you can probably guess what happened next. After the Tay disaster, after the inquiry revealed just how badly Bouch had underestimated wind loads and how poorly the construction had been supervised, his Forth Bridge design was immediately scrapped. Bouch himself was publicly disgraced. He died in 1880, just months after the inquiry, a broken man. It's one of those stories where you feel the weight of what engineering failure can do, not just to the people on the bridge, but to the person who designed it. The project was handed to two engineers, John Fowler and Benjamin Baker, and Baker, in particular, is someone worth knowing about. He was one of those engineers who combined deep theoretical knowledge with an obsessive attention to practical detail. He understood the math, he understood materials, and, crucially, he understood what had gone wrong at Tay. He wasn't just going to design a bridge that was strong enough. He was going to design a bridge that was so obviously, visibly, almost aggressively strong that no one would ever question whether it could stand. And here's where torque and bending moments become the entire design philosophy. Think about what a cantilever is. You already know this from Galileo's beam sticking out of a wall. A cantilever is a structure that's supported at one end and free at the other. When you load the free end, you create a bending moment at the support. The farther from the support the load is, the bigger that moment gets. Now, Baker's insight, building on centuries of structural understanding, was to use this principle deliberately, almost theatrically. The Forth Bridge consists of 3 massive towers, each one anchored to a small island or pier in the Firth. From each tower, 2 cantilever arms reach out in opposite directions, like a person extending both arms to the sides. The arms from adjacent towers almost meet in the middle, and short connecting spans bridge the remaining gaps. Here's what's clever about this. Each tower is essentially a balanced cantilever. The weight and forces on one arm are counterbalanced by the weight and forces on the other arm. Think of it like a seesaw that's perfectly balanced at the pivot. The bending moments created by the load on one side are counteracted by the bending moments on the other side. The tower itself, the pivot point, handles the compression. It pushes straight down into the foundation. And because the cantilever arms are mirror images of each other, the tower doesn't experience the kind of unbalanced twisting or toppling force that would be the real danger. Baker actually demonstrated this principle in a famous photograph. You might have come across it. He had 2 men sit in chairs, extending their arms outward while gripping sticks. A third man sat on a board suspended between their outstretched hands, representing the connecting span. The 2 seated men were the cantilever towers, their arms were the cantilever beams, and the guy in the middle was the load on the bridge. It's a wonderfully simple demonstration of a concept that, in practice, required thousands of tons of steel and millions of rivets to execute. Now, let's talk about those forces in a bit more detail, because this is where it gets really satisfying. When a train rolls onto one of the cantilever arms, it creates a bending moment that tries to pull the top of the arm into tension and push the bottom into compression, or vice versa, depending on the geometry. Baker designed the structure so that the top members of each cantilever arm are tubes, big, circular steel tubes that handle tension beautifully. The bottom members are also tubes, handling compression. And here's the thing about tubes. Remember when we talked about Euler's buckling formula and how the moment of inertia of a cross-section determines its resistance to buckling? A tube is one of the most efficient shapes you can use because all the material is pushed out to the maximum distance from the center. It gives you a high moment of inertia for relatively little material. So Baker wasn't just building big, he was building smart. Every piece of the fourth bridge is shaped and positioned to handle the specific type of force, tension, compression, or shear that it experiences at that exact location. The numbers are staggering. The bridge is about 2.5 kilometers long in total. Each of the two main spans, the gaps between the three towers, is over 500 meters. When it was completed in 1890, it was the longest cantilever bridge in the world by a huge margin. It used over 50,000 tons of steel and about 6.5 million rivets. 6.5 million. Think about that. Every single one of those rivets is a connection, and every connection is a potential point of failure. Baker knew this. The Tay Bridge had failed at its connections, so the riveting on the fourth bridge was held to extraordinarily high standards. Teams of riveters worked in groups, one man heating the rivet to cherry red in a portable forge, another catching it in tongs and placing it in the hole, a third holding a heavy dolly against one end, while a fourth hammered the other end to form the head. The rhythm of it, the coordination. It was like a kind of industrial music, repeated millions of times over the 8 years of construction. And the human cost was real. Around 98 workers died during the construction of the fourth bridge. Working at height, in Scottish weather, with heavy steel components being lifted and positioned by cranes that were primitive by modern standards, it was extraordinarily dangerous work. Baker and Fowler were aware of this and implemented safety measures that were advanced for the time, including safety boats stationed in the water below. But the reality of late 19th century construction was that large projects consumed lives. It's a sobering counterpoint to the engineering triumph, and it's worth sitting with that for a moment. But the bridge stood. It stood against everything the Scottish weather could throw at it. And it stood because Baker had designed it with wind loading at the very center of his calculations. Not as an afterthought, not as a rough estimate, but as a primary design driver. He used wind pressure values of 56 pounds per square foot, far more conservative than anything Booch had considered for the Tay Bridge. He tested models in wind conditions. He thought about how the wind would interact with the complex geometry of the bridge, not just pushing against flat surfaces, but creating turbulence, vortices, oscillating pressures. The bridge was designed to handle these dynamic forces, these constantly changing torques and moments, without distress. And this brings us to something important about how engineering thinking was evolving during this period. The fourth bridge wasn't just a triumph of steel and rivets. It was a triumph of a new way of thinking about structures, thinking about them not as static objects sitting quietly under their own weight, but as dynamic systems constantly interacting with their environment. Wind, temperature changes causing thermal expansion and contraction, the rhythmic pounding of trains, the slow settlement of foundations. All of these create forces that change over time, that cycle back and forth, that can gradually fatigue materials even when no single load exceeds the design limit. This idea of fatigue, the notion that a material can fail under repeated loading well below its ultimate strength, was something engineers were just beginning to grapple with in the late 1800s. A German engineer named August Wöhler had done pioneering work on metal fatigue in the 1850s and 1860s, largely motivated by failures in railway axles. Think about a railway axle for a second. It's a shaft, a round bar, that rotates under the weight of the train car. As it rotates, any given point on the surface of the axle alternates between being in tension on one side and compression on the other. Every single revolution is one complete stress cycle. A train axle might rotate millions of times in its service life, and Wöhler discovered that steel and iron could crack and eventually break after enough of these cycles, even if the stress in each individual cycle was well within what the material could handle in a single static test. This was a profound insight, and it connects directly back to torque. Because what is a rotating axle experiencing? Bending moments. The weight of the train car creates a bending moment at the axle, and as the axle rotates, that bending moment effectively cycles the stress at every point in the cross-section. Wöhler developed what we now call SN curves, plots of stress amplitude versus the number of cycles to failure, and these curves showed something that surprised a lot of people. For steel, there appeared to be an endurance limit, a stress level below which the material could theoretically withstand an infinite number of cycles without failing. But above that limit, even slightly above it, failure was just a matter of time. This changed everything about how engineers designed rotating machinery: axles, shafts, crankshafts, turbine blades, anything that experiences cyclic loading. And it's still absolutely central to engineering today. Every time you fly in an airplane, the wings are experiencing cyclic loading, flexing up and down with gusts, with turbulence, with the change from ground to air and back. The fuselage is being pressurized and depressurized with every flight cycle. Engineers design these structures with fatigue, life in mind, scheduling inspections at specific intervals, replacing components before they reach their predicted fatigue limit. But here's where it gets tricky, and where some of the most dramatic engineering failures of the 20th century come into the story. Because fatigue doesn't always behave the way you'd expect. Cracks don't always start where you predict. Stress concentrations, places where the geometry of a part creates a local spike in stress, like a sharp corner, a hole, a notch, or even a scratch on the surface, can dramatically reduce fatigue life. And in the early days of jet aviation, this lesson was learned in the most painful way possible. The aircraft was the de Havilland Comet, and what happened to it would become one of the most important case studies in the entire history of engineering. The Comet was, by every measure, a marvel. When it first flew commercially in May of 1952, operated by BOAC, British Overseas Airways Corporation, it was the world's first commercial jet airliner. And it wasn't just first by a little bit. It was years ahead of anything Boeing or Douglas had in the pipeline. The Comet cruised at over 500 miles per hour, nearly twice the speed of the propeller-driven airliners it was replacing. It flew higher, too, above most of the weather, at altitudes around 36,000 feet. Passengers described the experience as almost surreal, smooth, quiet compared to the bone-rattling vibration of piston engines, and fast. London to Johannesburg in under 24 hours with stops, a journey that used to take days. Britain was justifiably proud. After the devastation of the Second World War, after years of austerity and rationing, here was proof that British engineering was still world-class. The Comet was a symbol of national renewal, and then it started falling out of the sky. The first loss that really shook people was BOAC Flight 783, which broke apart in flight on May 2, 1953, shortly after taking off from Calcutta. All 43 people on board were killed. The wreckage fell near the village of Jagalgori. Initial investigations pointed toward a possible structural failure during a severe storm, and while the Comet fleet was briefly grounded for inspections, it was put back into service. Then, on January 10, 1954, BOAC Flight 781 disintegrated over the Mediterranean Sea near the island of Elba about 20 minutes after departing Rome. 35 people died. The fleet was grounded again, modifications were made, and again the Comets returned to service. And then, just weeks later, on April 8, 1954, another Comet, South African Airways Flight 201, also operated on behalf of BOAC, broke apart over the Mediterranean near Naples. 21 people killed. That was it. The Comet was grounded permanently, and what followed was one of the most thorough and groundbreaking accident investigations in aviation history. Here's what makes this story so important from an engineering perspective. The investigators, led by a team at the Royal Aircraft Establishment at Farnborough, essentially had to invent new methods of failure analysis to figure out what was going wrong. They recovered as much wreckage as they could from the Mediterranean, a painstaking process involving naval vessels and early sonar technology, pulling pieces of twisted aluminum from the seabed. They reconstructed the fuselage of the Elba crash aircraft piece by piece in a massive hangar, like assembling a three-dimensional jigsaw puzzle of shattered metal. And they did something else that was remarkable. They took an entire intact Comet fuselage, placed it in a giant water tank at Farnborough, and subjected it to repeated pressurization cycles to simulate the stresses of flight after flight after flight. They filled the fuselage with water instead of air for safety. If it failed while pressurized with air, the explosive decompression would be catastrophic. But water is essentially incompressible, so a water-filled fuselage would fail much more gently. Clever, right? And they cycled it. Pressurize, depressurize. Pressurize, depressurize. Over and over, simulating the life of an aircraft flying at high altitude. After the equivalent of about 9,000 flight cycles, the test fuselage failed. A crack appeared at the corner of one of the rectangular window cutouts, propagated rapidly through the skin, and the fuselage burst open. And when they examined the wreckage recovered from the Mediterranean, they found the same thing. Fatigue cracks originating at the corners of the windows, specifically at rivet holes near those corners, where the geometry created intense stress concentrations. Now, think about what's happening here in terms of the concepts we've been building up. Every time the Comet climbed to cruising altitude, the cabin was pressurized to keep the passengers comfortable. The pressure inside the fuselage was significantly higher than the near vacuum outside at 36,000 feet. That pressure difference created hoop stress in the fuselage skin, tension pulling the skin apart circumferentially, like blowing up a balloon. And every time it landed, that pressure was released, so the fuselage skin was being cycled in tension, loaded, unloaded, loaded, unloaded, with every single flight. That's fatigue loading, exactly the kind of thing Wöhler had studied a century earlier with railway axles. But here's where the stress concentration piece becomes critical. The Comet had large, nearly square windows with relatively sharp corners. If you imagine the stress flowing through the fuselage skin like water flowing in a stream, and then you put a square hole in the middle of that stream, the stress has to flow around the hole. At the corners of a square hole, the stress gets squeezed into a tiny area, and the local stress can be several times higher than the average stress in the surrounding skin. Engineers call this a stress concentration factor, and for a sharp corner, it can be enormous. 3 times, 4 times, even higher than the nominal stress, depending on the geometry. So even though the average stress in the fuselage skin might have been well within the material's endurance limit, the local stress at those window corners was far above it. Fatigue cracks initiated there, grew a little with each flight cycle, and eventually reached a critical length where the remaining material couldn't hold, and the crack propagated catastrophically across the fuselage in a fraction of a second. Explosive decompression, structural disintegration at altitude. And here's a painful detail. The Comet's windows had been designed with what were called AV rivet holes at the corners, small holes drilled for the attachment of the window frames. These holes had been punch riveted rather than drill riveted in some cases, a manufacturing process that could leave tiny burrs and micro cracks around the hole edges. So you had a geometric stress concentration from the square corner, made even worse by microscopic surface damage from the manufacturing process. It was a perfect storm of factors that nobody had fully appreciated, because nobody had ever built a pressurized jet airliner before. The loads were new. The altitude was new. The number of pressurization cycles that would accumulate over a commercial service life was new. The Comet was exploring territory where the existing engineering knowledge simply wasn't sufficient. The aftermath of the Comet investigations reshaped aircraft design permanently. Future airliners, including the Boeing 707, which would go on to dominate the jet age, used oval or round windows with generous radii at every corner, specifically to minimize stress concentrations. Fuselage structures were designed with fail-safe principles, meaning that if a crack did develop, the structure was designed to arrest it before it could propagate catastrophically. Tear straps, crack stoppers, redundant load paths, all of these became standard features of aircraft design, and all of them traced directly back to the lessons of the Comet. And this connects back to something deeper about how engineering evolves. The Comet wasn't a badly designed airplane. It was designed by talented engineers using the best knowledge available at the time. Geoffrey de Havilland's company had built some of the most iconic aircraft of the Second World War. The Mosquito, that extraordinary wooden wonder. They knew structures, they knew aerodynamics, but they were pushing into a regime where the existing design rules didn't fully apply, and the gaps in understanding were invisible until they manifested as cracks propagating through aluminum skin at 36,000 feet. That's the nature of engineering at the frontier. You don't always know what you don't know. So let's sit with that idea for a moment, because it connects to something broader about torque, stress, and structural failure that runs through everything we've been talking about. From Galileo puzzling over why larger beams break under their own weight, to Euler working out the mathematics of buckling, to Navier figuring out where the neutral axis sits in a bending beam, to Bouch's cast iron columns failing in the Tay Bridge storm, to Baker's team driving 6.5 million rivets into the fourth bridge, to Wöhler plotting his SN curves for railway axles, to the Comet investigators pulling wreckage from the Mediterranean. There's a single thread. Engineers are always trying to understand how forces distribute through materials and structures, where the weak points are, and how failure begins. Torque, bending moments, stress concentrations, fatigue. These aren't separate topics. They're all facets of the same fundamental question. How does a structure carry load, and when does it stop being able to? And that question takes on a whole new dimension when you start thinking about materials themselves. Because up to now, we've mostly been talking about steel and iron and aluminum, metals that behave in relatively predictable ways. At least once, you understand their properties. But the 20th century brought a revolution in materials that completely changed how engineers think about torque, bending, and structural design. I'm talking about composites. Materials like fiberglass, and eventually carbon fiber reinforced polymers. And to understand why composites matter so much, you need to understand something about how materials resist bending at the microscopic level. Think back to Navier's beam theory. When a beam bends, the material on one side is in tension, the material on the other side is in compression, and there's a neutral axis in between where the stress is zero. The farther you get from that neutral axis, the higher the stress. That's why I-beams work. You put the material where the stress is highest, out at the flanges, and use just a thin web to connect them. But here's the thing about metals. They're isotropic, meaning their mechanical properties are the same in every direction. A chunk of steel is equally strong whether you pull on it this way or that way. It doesn't care about orientation. Composites are fundamentally different. Carbon fiber, for instance, is extraordinarily strong and stiff along the length of the fiber. We're talking about a tensile strength that can be 5 or even 10 times that of steel at a fraction of the weight. But perpendicular to the fiber, it's relatively weak. The strength depends entirely on direction. Engineers call this anisotropy, and it means that when you're designing a composite structure, you're not just choosing a material. You're designing the material itself, laying fibers in specific orientations to resist loads in specific directions. And this is where torque gets really interesting in the context of composites, because when you apply a twisting load to a composite tube or shaft, the way the fibers are oriented relative to the twist axis completely determines how the structure responds. If you wind the fibers at 45 degrees to the axis, you maximize torsional stiffness because the twist creates shear stress, and fibers at 45 degrees are perfectly aligned to resist shear. But if you laid those same fibers at 0 degrees, straight along the length, you'd have tremendous bending stiffness, but relatively poor torsional resistance. So composite drive shafts, helicopter rotor blades, wind turbine blades, aircraft wing skins, all of these are designed with specific fiber layup schedules that are tuned to the exact combination of bending, torsion, and axial loads the structure will experience. It's like being able to customize the grain of wood, except with materials that are stronger than steel and lighter than aluminum. The person who arguably did more than anyone to bring composite structures into mainstream aerospace was a quiet, methodical engineer at NASA's Langley Research Center. And the story of how carbon fiber composites went from laboratory curiosity to the primary structural material in modern airliners like the Boeing 787 is one of those slow burn engineering revolutions that changed everything without anyone really noticing until it was already done. Because that's how it happened. It wasn't a single dramatic moment. It was decades of patient testing, skepticism, small victories, and a whole lot of people being told that metal was good enough, that composites were too expensive, too unpredictable, too new. The engineer at the center of a lot of this work was a man named Marvin B. Dow, though honestly, the composite revolution at Langley was really a team effort spanning the 1970s and 80s. What Dow and his colleagues were trying to do was answer a deceptively simple question. Can we build real aircraft structures out of carbon fiber reinforced polymer and trust them to survive 20, 30 years of service? Not lab specimens, not test coupons. Real parts on real planes, flying through real weather, taking real hits from hailstones and runway debris, and the 1,000 little insults that an airplane endures over its lifetime. And the answer wasn't obvious, because carbon fiber composites behave in ways that are fundamentally different from metals. And a lot of those differences are, Frankly, a little unsettling if you're an engineer trained to think in terms of aluminum. Here's the thing about aluminum. And this connects back to everything we talked about with Wöhler and fatigue and the comet. When aluminum starts to fail, it usually gives you warning signs. A crack forms, it grows slowly, you can inspect for it, you can catch it before it becomes catastrophic. That's the whole basis of the damage-tolerant design philosophy that came out of the comet disasters. You assume cracks will form. You design the structure so they grow slowly, you inspect at regular intervals, and you replace parts before the cracks reach critical length. It's a well-understood, well-tested approach, and it works beautifully for metals. But composites don't crack the same way. They don't form neat little fatigue cracks that propagate in predictable paths. Instead, they tend to accumulate damage in more diffuse, harder-to-detect ways. You might get delamination, where the layers of the composite start to separate from each other internally. You might get matrix cracking, where the resin between the fibers develops tiny fractures that you can't see from the surface. And here's what really worried people. You could have significant internal damage in a composite structure with almost no visible indication on the outside. Someone could drop a tool on a composite panel during maintenance, and the surface might look fine, maybe a tiny dent, maybe nothing at all. But inside, the layers could be separating over an area the size of your hand, and that hidden damage could reduce the panel's ability to carry compressive loads by 30, 40, even 50%. Think about what that means for a moment. With metal, you can tap on it, look at it, run a dye penetrant test, and you'll find surface cracks. With composites, the danger is invisible. So the whole inspection philosophy that the aviation industry had spent decades perfecting for metal aircraft suddenly didn't apply. You needed entirely new methods, ultrasonic inspection, thermography, sometimes even sophisticated techniques that could peer inside the layup without cutting it open. And you needed to understand, quantitatively, how much hidden damage a composite part could tolerate and still carry its design loads. This is what NASA Langley spent years figuring out. They ran what they called the Aircraft Energy Efficiency Program, starting in the mid-1970s, and one of its components focused specifically on getting composite structures onto commercial aircraft. Not the whole airplane, not yet, but secondary structures first. Fairings, control surfaces, spoilers, elevators. Parts where a failure wouldn't bring down the airplane, but where you could accumulate real-world service data. They partnered with Boeing, Lockheed, and Douglas, and they got composite components flying on commercial aircraft. Things like the 737 spoiler, made from carbon fiber reinforced epoxy that entered service around 1973. And then they watched. They tracked those parts for years, even decades, periodically pulling them off airplanes and testing them in the lab to see how they'd held up. And here's what's really satisfying about this story. The parts held up remarkably well. After 10, 15, 20 years of airline service, the composite components retained the vast majority of their original strength. The fears about long-term degradation, about moisture absorption slowly weakening the resin, about thermal cycling causing progressive damage. Those fears turned out to be manageable, not non-existent, but manageable. The data from those long-term service evaluations gave the industry the confidence it needed to start thinking bigger, not just spoilers and fairings, primary structure, wings, fuselage barrels, the parts that hold the airplane together. But confidence in the material was only half the battle. The other half was figuring out how to design with it efficiently, And this is where the torque story gets really rich, because aircraft structures are subjected to some of the most complex combinations of loading you can imagine. Think about an airplane wing. It's being bent upward by lift forces. It's being twisted by aerodynamic loads that shift as the plane maneuvers. It's being compressed and stretched by pressurization of the fuselage it's attached to. It's vibrating. It's experiencing gusts. It's going through thermal cycles as the plane climbs into -50-degree air and then descends back to a hot tarmac. All of these loads are happening simultaneously, and they're constantly changing. Now, with an aluminum wing, you design the structure, the spars, the ribs, the skin panels, and the material responds the same way in every direction. Isotropic, remember? You just need to make sure the stresses stay below allowable limits everywhere. But with a composite wing, you have this extraordinary ability and this extraordinary responsibility to tailor the layup at every location on the wing to match the local loading. Near the root of the wing, where bending moments are highest, you might stack more fibers along the span to resist bending. Out toward the tip, where torsion becomes more significant relative to bending, you might increase the proportion of plus and minus 45-degree plies. On the upper skin, which is primarily in compression during flight, you might use a different layup than on the lower skin, which is primarily in tension. You're essentially creating a different material at every point on the structure, optimized for exactly what that point needs to do. And this is where it gets genuinely beautiful from an engineering standpoint. There's a phenomenon called aeroelastic tailoring, and it's one of those ideas that could only exist because of composites. Here's the concept. When a wing bends upward under load, it also tends to twist. In a conventional metal wing, the direction of that twist is determined by the geometry, the position of the aerodynamic center relative to the structural axis, and you're basically stuck with whatever twist the geometry gives you. But with composites, you can design the layup so that bending and twisting are coupled in a way you choose. You can make a wing that, when it bends up in a gust, automatically twists to reduce its angle of attack, which reduces the lift on that section, which reduces the bending load. The wing essentially alleviates its own loads. It's a self-correcting structure, and it's possible because the anisotropy of the composite, the very property that makes design so complicated, can be harnessed as a feature rather than a limitation. This idea was explored extensively in research programs through the 80s and 90s, and it represents a fundamental shift in how engineers think about the relationship between structure and aerodynamics. In the metal world, you design the aerodynamic shape, then you design a structure strong enough to hold that shape under load. In the composite world, the structure and the aerodynamics become intertwined. The structure's response to load changes the aerodynamic shape, which changes the load, which changes the structural response. It's a coupled system, and getting it right requires analytical tools that would have been unimaginable to someone like Navier or even the Fourth Bridge engineers. So when Boeing finally committed to making the 787 Dreamliner with a fuselage and wings that were approximately 50% composite by weight, this was announced around 2003, with the first flight coming in December 2009. It was the culmination of all of this. 30-plus years of testing, of service data, of analytical method development, of manufacturing process refinement. The 787's fuselage is built in large barrel sections using a process called automated fiber placement, where a robotic head lays down thin strips of carbon fiber pre-impregnated with resin onto a cylindrical tool, building up the barrel layer by layer. Each strip is placed at a precisely controlled angle, and the layup schedule varies around the circumference and along the length of the barrel to match the local stress state. The whole barrel is then cured in an autoclave, essentially a giant pressure cooker, and what comes out is a one-piece fuselage section with no longitudinal joints. Compare that to a conventional aluminum fuselage, which is assembled from hundreds of individual skin panels, stringers, and frames, all connected by thousands of fasteners, each one of which is a potential site for fatigue crack initiation. The composite barrel eliminates most of those joints and fasteners, which is a huge advantage for fatigue life and also for pressurization efficiency, because the barrel acts like a seamless pressure vessel. And here's a practical detail you'd appreciate. Because the composite fuselage doesn't fatigue the same way aluminum does under pressurization cycles, Boeing was able to increase the cabin pressure altitude in the 787 to the equivalent of 6,000 feet, compared to 8,000 feet in most conventional aluminum airliners. That might not sound like much, but it makes a real difference in how you feel after a long flight. Less dehydration, less fatigue, fewer headaches. The material science of carbon fiber composites literally changes the air you breathe at 35,000 feet. But let's pull back for a moment, because I want to make sure we don't lose sight of the deeper thread here. Everything we've been talking about, from Archimedes' lever, through Galileo's cantilever, through the Tay Bridge, and the Fourth Bridge, through Wöhler's fatigue curves, and the comet's square windows, through composite layup schedules and aeroelastic tailoring. All of it comes back to one fundamental question. How do forces move through structures, and how do structures eventually fail? Torque is one of the most important manifestations of that question because twisting loads are everywhere, and they're often the sneakiest. Bending is intuitive. You can see a beam sag. You can feel a shelf bow under too many books. But torsion is subtle. It hides inside shafts, inside wings, inside the connections between components. And when torsional failure happens, it can be sudden and violent because the shear stresses involved act on planes that aren't always obvious. Which brings me to something I've been wanting to talk about, because it's one of the most dramatic examples of torsional failure in engineering history, and it happened not in an airplane or a bridge, but in something you might not immediately associate with torque at all. I'm talking about the failure of the molasses storage tank in Boston's North End on January 15, 1919, an event so bizarre and so devastating that it sounds like fiction. A massive steel tank, 50 feet tall and 90 feet in diameter, holding over 2 million gallons of crude molasses, suddenly and catastrophically ruptured, sending a wave of molasses through the streets at an estimated 35 miles per hour. 21 people were killed. 150 were injured. Buildings were knocked off their foundations. The elevated railway structure was damaged. And when investigators finally pieced together what happened, the story they found was one of negligence, of corner cutting, and of a structure that was never adequate for the loads it carried from the very beginning. So, here's the setup. The Purity Distilling Company built this tank in 1915, right along the waterfront in Boston's North End, which was a densely packed, residential neighborhood, mostly Italian immigrants, working-class families, tenement buildings pressed close together. The tank was enormous. We're talking about a riveted steel cylinder, roughly 90 feet across and 50 feet tall, holding about 2.5 million gallons when full. The molasses stored inside was used for industrial alcohol production, and in the years during and just after World War I, demand for industrial alcohol was enormous because it was a key ingredient in munitions manufacturing. So this tank was kept full, often topped off with fresh shipments arriving by ship. And on January 15, 1919, It had been recently filled to near capacity with a fresh delivery of warm molasses from the Caribbean. Now here's where the engineering story gets interesting, and where torque enters the picture in a way you might not expect. Think about what's happening inside a tank like this. You've got a massive volume of dense liquid. Molasses is significantly heavier than water, roughly 1.5 times as dense, pressing outward against the walls. That outward pressure creates what engineers call hoop stress in the cylindrical shell. Imagine wrapping a rubber band around a balloon and then inflating the balloon further. The rubber band stretches, and the tension in it is analogous to hoop stress. In a cylindrical tank, the hoop stress is proportional to the pressure times the radius divided by the wall thickness. Bigger tank, thinner walls, more pressure, higher stress. Straightforward enough. But here's the thing. A real tank isn't a perfect, infinite cylinder floating in space. It's bolted to a foundation. It has a bottom plate. It has manhole covers and fill pipes and discharge valves, all of which are discontinuities, places where the smooth flow of stress gets interrupted and concentrated. And the tank isn't loaded uniformly either. The hydrostatic pressure from the molasses is highest at the bottom, where the full weight of the liquid above is pressing outward, and lowest at the top. So the stress distribution varies along the height of the wall. The bottom courses of steel plate carry the highest hoop stress and need to be the thickest. And this is where the Purity Distilling Company's tank was already in trouble before it ever failed. The original construction was supervised by Arthur Gell, a treasurer of the company who had no engineering background whatsoever. He couldn't read blueprints. He chose the steel plate thickness not through careful stress analysis, but apparently through a combination of cost minimization and guesswork. The walls were too thin, particularly in the lower courses where the loads were greatest. Some accounts suggest the steel was only about 2/3 the thickness it should have been for the pressures involved, and the steel itself may have been of poor quality, more brittle than it should have been, with a higher transition temperature, meaning it became more prone to sudden fracture in cold weather. But wait, you might be thinking, where does torsion come into this? It's a cylindrical tank. The loads are radial pressure and gravity. Where's the twisting? And this is what makes this case so instructive, because the answer is, torsion was hiding in the details, the way it so often does. The tank wasn't sitting on flat, open ground. It was built on a sloping site, wedged between a fire station, a playground, residential buildings, and the elevated railway. The foundation wasn't perfectly level. The tank was anchored asymmetrically, and as the tank was filled and emptied repeatedly over its 4-year life, the differential settlement of the foundation and the asymmetric restraint at the base created secondary stresses that included torsional components, shear stresses acting in the plane of the tank wall that the original design, such as it was, never accounted for. Even more importantly, think about what happens at the riveted seams. This tank was built from curved steel plates riveted together, both in vertical seams running up the height and horizontal seams running around the circumference. Every single one of those rivet holes was a stress concentration, and at the lap joints, where one plate overlapped another, the load transfer through the rivets created local bending and shear, essentially tiny torsional moments at every connection point. If you imagine 2 plates riveted together and then pulled in tension, the offset between the plate center lines means the load path isn't straight. It has to jog sideways through the rivet, and that eccentricity creates a bending moment. Scale that up to thousands of rivets around a pressurized tank, and you've got a structure riddled with local stress concentrations where fatigue cracks can nucleate and grow. And the evidence suggests that's exactly what was happening. Residents in the neighborhood had reported the tank leaking for years. Molasses seeped from the riveted seams so regularly that local children would collect it in cups. The company's response was not to investigate or reinforce the structure, but to paint the tank brown so the leaks would be less visible. Think about that for a moment. A tank holding 2.5 million gallons of dense liquid in a crowded neighborhood, visibly leaking from its seams, and the engineering response was cosmetic. On the morning of January 15, 1919, the temperature in Boston had risen sharply, from near zero the previous few days to about 40 degrees Fahrenheit. The tank had been recently filled with warm molasses, perhaps around 50 degrees or warmer from its Caribbean origin. The combination of the warm liquid expanding slightly, the internal pressure from fermentation gases, molasses ferments and produces carbon dioxide, adding to the pressure inside the tank, and the already overstressed, crack-riddled structure proved catastrophic. Sometime around noon, the tank let go. And when I say let go, I mean it came apart almost instantaneously. The failure initiated near the base, where the stresses were highest, likely at a rivet line where a fatigue crack had been growing for months or years. Once the crack reached a critical length, it propagated through the brittle steel at enormous speed. This is exactly the kind of fast fracture we talked about with the de Havilland Comet, where a crack that's been growing slowly under cyclic loading suddenly hits a critical size, and the material just unzips. The steel plates tore apart, and the full contents of the tank, about 12,000 metric tons of molasses, surged outward in a wave that witnesses described as 15 to 25 feet high. The physics of that wave are worth pausing on because it helps you understand why this wasn't just a messy spill. Molasses is a non-Newtonian fluid. Its viscosity depends on temperature and shear rate. When it first burst from the tank, driven by enormous pressure and moving fast, it behaved almost like water, flowing rapidly through the narrow streets. The initial wave had enough momentum to buckle the steel support columns of the elevated railway, push a fire station off its foundation, and crush wooden tenement buildings. People caught in the wave were trapped. And then, as the molasses spread and slowed, its viscosity increased, making it progressively harder for rescuers to move through. Horses, dogs, and people were mired in a thickening mass that was extraordinarily difficult to escape. The aftermath was devastating, and the investigation that followed was groundbreaking. The resulting lawsuit, one of the longest civil proceedings in Massachusetts history at that time, stretching from 1920 to 1925, produced testimony from some of the leading structural engineers and metallurgists of the era. The court-appointed auditor, Hugh Ogden, ultimately found the Purity Distilling Company liable, concluding that the tank had been inadequately designed and built, that the company had ignored clear warning signs of structural distress, and that the steel was insufficient for the loads imposed. But here's what makes the Boston molasses flood resonate beyond its own time. It became one of the catalysts for requiring that engineering designs be certified by licensed professional engineers. Before this disaster, there was no consistent requirement in Massachusetts, or in most of the United States, that structures holding dangerous materials be designed and approved by qualified engineers. Arthur Gell, the company treasurer with no engineering training, had overseen the construction of a massive, pressurized vessel in a residential neighborhood, and nobody had the regulatory authority to stop him. The disaster helped change that. It contributed to the movement toward professional engineering licensure laws that were adopted across the United States in the following decades. So you can draw a straight line from the Boston molasses flood to the PE stamp that appears on engineering drawings today. That stamp means a licensed professional engineer has reviewed the design and taken personal legal responsibility for its adequacy. It's a direct consequence of disasters like this one, where the absence of qualified oversight cost lives. And this connects to something larger that I think is really worth sitting with for a moment. Throughout everything we've talked about, the Tay Bridge, the comet, the molasses tank, there's a recurring pattern. The engineering knowledge to prevent each disaster existed at the time it happened. Navier's stress analysis was available decades before the Tay Bridge fell. Pressurization fatigue was a known concern before the comet flew. The basic principles of hydrostatic pressure and hoop stress were well understood in 1915. The failures weren't failures of science. They were failures of application, of communication, of oversight, of institutional will. Someone either didn't know what they should have known, or knew it and was overruled by cost pressure, or wasn't in a position of authority to act on their knowledge. That's why the regulatory and professional frameworks around engineering matter just as much as the technical knowledge itself, the math of torque, the physics of stress concentration, the metallurgy of fracture toughness. None of it helps if it doesn't reach the person making the decision about how thick to make the steel plate. Now, speaking of decisions about materials and thickness, there's another domain where torsion plays a starring role that you interact with literally every day, probably without thinking about it at all. And that's the automobile. Specifically, the chassis, the structural skeleton of every car and truck on the road. Because the single most important structural property of a vehicle chassis is its torsional rigidity. How much does the frame twist when one wheel hits a bump and the others don't? And the story of how automotive engineers learn to design for torsional stiffness is fascinating, because it tracks almost perfectly with the broader evolution of structural understanding that we've been following all along. The earliest automobiles, in the late 1890s and early 1900s, were essentially horse carriages with engines bolted on, and their frames were built exactly the way carriages had been built for centuries. Two long parallel rails of wood or simple channel iron, connected by a few cross members, with everything just sort of sitting on top. And here's the thing about those early ladder frames, as they came to be called. They were designed to handle bending loads, the weight of the engine, the passengers, the cargo pressing down, the wheels pushing up. That's a bending problem, and the ladder frame handled it reasonably well. But torsion? Nobody was really thinking about torsion. And why would they? Horse carriages moved slowly over rutted roads, and the suspension, such as it was, consisted of leaf springs that allowed the body to flex and rock. A little twist in the frame didn't matter much when your top speed was walking pace. But then engines got more powerful, roads got rougher before they got smoother, and speeds climbed from 10 miles an hour to 20, then 30, then 40. And suddenly that twist in the frame mattered enormously. Picture this. You're driving along and your front right wheel drops into a pothole. That corner of the car dips, but the other three wheels are still on flat ground. What's happening to the frame? It's being twisted. One corner is being forced down while the diagonally opposite corner stays up, and the entire structure is experiencing a torsional load. If the frame is floppy, if it has low torsional rigidity, the whole car flexes like a wet noodle. Doors won't close properly because their openings have gone from rectangles to parallelograms. The suspension can't do its job because the frame is absorbing the movement instead of letting the springs and dampers handle it. The car feels vague and wallowy, And at higher speeds it becomes genuinely dangerous because the chassis is twisting and untwisting in ways that interfere with steering and handling. Early automotive engineers figured this out the hard way. Through the 19-teens and 20s, as cars got faster and heavier, chassis flex became a serious problem. And the solution, initially, was brute force. Make the frame rails deeper, make them thicker, add more crossmembers. But that added weight, which demanded a bigger engine, which added more weight, which demanded an even stiffer frame. You can see where that spiral goes. The real breakthrough in understanding came gradually, and it's tied to a concept we've been circling around this whole time: the closed section versus the open section. Think about it this way. Take a piece of paper and roll it into a tube. That tube is remarkably resistant to twisting. Now take the same piece of paper and fold it into a C shape like a channel or a gutter. Try to twist that. It's floppy. It twists easily. The difference is dramatic, and the reason is fundamental to how torsion works in thin-walled structures. When you twist a closed tube, the shear stresses flow in a continuous loop around the wall. They chase each other around and around in a complete circuit, and the material resists the twist efficiently. But when you twist an open section like a C-channel, the shear stresses can't complete that loop. They have to reverse direction, flowing one way along the top flange, back the other way along the web, and out along the bottom flange. The section warps, it distorts, and it's dramatically less stiff in torsion. We're talking orders of magnitude less stiff. A closed square tube might be 100 or even 1,000 times more torsionally rigid than an open channel of the same dimensions and wall thickness. And here's the kicker. Those early ladder frames were made entirely of open section channel rails. Wide open C channels, facing inward or outward, connected by cross members that were often also open sections. The whole thing was essentially designed to be weak in torsion, not on purpose, but because nobody was applying torsional analysis to car frames yet. The knowledge existed. The mathematics of torsion in thin-walled sections had been worked out by Adhémar Jean-Claude Barré de Saint-Venant back in the 1850s and later refined by others. But just like the Tay Bridge, just like the molasses tank, the knowledge wasn't reaching the people making the decisions. Early car builders were craftsmen, blacksmiths, carriage makers, brilliant, practical people, but not structural analysts. The shift started happening in the late 1920s and especially the 1930s, and it came from an unexpected direction: aviation. Aircraft designers had been dealing with torsion from the very beginning because an airplane wing that can't resist twisting is an airplane that crashes. The early biplanes handled torsion with their network of struts and wire bracing, essentially triangulating the structure so that torsional loads got converted into tension and compression in the wires and struts. But as monoplanes took over in the late 20s and 30s, designers needed the wing skin itself to carry torsional loads. This led to what's called stressed skin construction. The idea that the outer skin of a structure isn't just a covering, it's a load-bearing element. And a closed skin, wrapped around the wing like a tube, creates exactly that efficient, closed-section torsional path we were just talking about. Now, automotive engineers started borrowing this idea. The person most associated with bringing aircraft structural thinking to cars is Vincenzo Lancia, the Italian manufacturer. In 1922, Lancia introduced the Lambda, which is widely considered the first production car, with a load-bearing unitary body structure. Instead of a separate ladder frame with a body bolted on top, the Lambda used the body panels themselves as structural elements, creating something much closer to a closed box. The torsional rigidity was dramatically better than anything else on the road. Lancia was an intuitive genius, a former racing driver and test driver for Fiat who had a feel for how cars should behave. And he understood, perhaps more by instinct than by calculation, that the body and frame needed to work together as one structure. But the real mathematical understanding of why unibody construction was so superior in torsion came later, particularly through the work of engineers at companies like Citroën and Porsche in the 1930s, and the broader adoption of aerospace structural analysis methods by the auto industry after World War II. During the war, tens of thousands of engineers learned to design aircraft structures, stressed skin fuselages, torsion boxes, monocoque shells, and, when they came home, they brought that knowledge with them into every other industry. The post-war era saw a massive shift toward unibody construction in passenger cars, and torsional rigidity became an explicit design target for the first time. And this is where it gets really interesting from an engineering standpoint, because measuring torsional rigidity in a car is beautifully straightforward. You bolt the chassis down at the rear axle mounting points, then you apply a known torque at the front axle, usually by jacking up one side and measuring how much the whole structure twists. The result is expressed in Newton meters per degree, or foot-pounds per degree. A typical modern sedan might have a torsional rigidity of 20,000 to 30,000 Newton meters per degree. A really stiff sports car might hit 40 or 50,000. And a Formula One car? Those carbon fiber monocoques we talked about earlier, the ones with fibers carefully oriented at 45 degrees for maximum torsional resistance? They can exceed 100,000 Newton meters per degree while weighing almost nothing. That's the payoff of understanding exactly how torsion works and designing every fiber, every ply, every bond line to resist it optimally. But you don't need to be driving a Formula One car to feel the effects of torsional rigidity. Think about the last time you drove over a speed bump at an angle, one wheel at a time. In a torsionally stiff car, the suspension compresses smoothly. The body stays composed, and the car feels solid and planted. In a less rigid car, maybe an older truck with a traditional ladder frame, you can sometimes feel the body shudder, hear the dashboard creak, maybe even see the door gaps change slightly. That's the frame twisting. That's torsion you can feel in your bones. And it's not just about comfort. Torsional rigidity directly affects safety. In a crash, you need the structure to deform in controlled, predictable ways. Crumple, zones at the front and rear absorbing energy while the passenger cell stays intact. If the chassis is torsionally floppy, crash forces get distributed unpredictably. The structure might fold where it shouldn't, or fail to fold where it should. Modern crash engineering depends absolutely on having a stiff, well-understood torsional baseline to work from. There's a wonderful irony here, too. The pickup truck, which for decades was the last holdout of the old ladder frame design, and for good reason, because a separate frame lets you bolt different bed configurations on top and handles the heavy payload and towing loads well. The pickup truck has become one of the most interesting battlegrounds for torsional engineering in the 21st century. As trucks transitioned from work vehicles to daily drivers and family haulers, buyers started expecting car-like ride quality and handling. And that meant truck engineers had to find ways to dramatically increase the torsional rigidity of what is fundamentally an open-section ladder frame. They did it with fully boxed frame rails, taking those old C-channels and welding plates across the open side to create closed rectangular tubes. They added hydraulic body mounts that decouple the cab from frame twist. They used computer optimization to place cross members at exactly the right locations to maximize torsional stiffness with minimum weight. Ford's move to an aluminum body on the F-150 in 2015 is a perfect example of how all these threads converge. The aluminum panels saved about 700 pounds, but aluminum behaves differently from steel in terms of how you join it. You can't just spot weld it the same way. So Ford used a combination of self-piercing rivets, structural adhesives, and flow drill screws, each chosen for specific locations based on the stress state at that point in the structure. And many of those joints are carrying torsional shear loads, which means the engineers had to understand not just the static, torsional rigidity, but the fatigue behavior of each joint type under millions of cycles of torsional loading. Remember Wöhler and his railroad axles? Same fundamental problem, applied to a truck body joint 150 years later. And that brings us to something that might seem like a completely different topic, but is actually deeply connected. The engineering of everyday objects that you twist with your hands. Because torsion isn't just about massive structures and vehicle chassis. It's about every doorknob you turn, every jar lid you unscrew, every wrench you grip. And there's one particular everyday application of torsion that engineers have spent a surprising amount of time and ingenuity perfecting. Something so common that you probably used one today without giving it a moment's thought. I'm talking about the humble bolt and nut, the most ubiquitous fastener in the engineered world, and a device whose entire function depends on a beautifully controlled application of torsion. When you tighten a bolt, what you're really doing is converting the rotational force you apply with a wrench, that's your torque, into a linear clamping force that pulls the two parts together. The bolt is essentially a simple machine, an inclined plane wrapped around a cylinder. Think of it like a spiral ramp. When you twist the bolt, the threads ride along that ramp, and the geometry of the helix converts your rotational input into axial stretch. The bolt actually elongates just a tiny amount, and it's that stretch, that elastic tension in the bolt shank, that creates the clamping force holding the joint together. The bolt wants to spring back to its original length, and that restoring force is what keeps everything tight. Now here's what's fascinating. When you torque a bolt, not all of your input torque goes into stretching the bolt. In fact, most of it doesn't. Roughly 85 to 90% of the torque you apply is lost to friction. Friction between the nut and the surface it's bearing against, and friction between the mating threads. Only about 10 to 15% of your applied torque actually becomes useful clamping force. That's a staggering inefficiency when you think about it. And it means that the relationship between how much torque you apply and how much clamping force you get is highly sensitive to the friction conditions. A little oil on the threads, a slightly different surface finish, a washer versus no washer. These seemingly trivial details can change the clamping force by 30 or 40% for the same applied torque. That's why torque specifications in engineering manuals often come with a footnote about lubrication conditions. A torque spec is only meaningful if you know the friction state. This is one of those places where torsion meets the real world in a way that has enormous consequences. Think about the lug nuts on your car wheels. There's a reason your owner's manual specifies a torque value, typically somewhere around 80 to 100 foot-pounds for a passenger car. Too little torque and the wheel can work loose, which is catastrophic. Too much torque and you can stretch the bolt past its yield point, weakening it. Or you can warp the brake rotor by creating uneven clamping pressure. Either way, The failure mode traces back to getting the torsion wrong. And in critical applications, aircraft engines, pressure vessels, bridges, engineers don't trust torque alone to determine bolt tension. They use more sophisticated methods. Ultrasonic bolt measurement, for instance, where you send a sound pulse down the length of the bolt and measure how long it takes to bounce back. As the bolt stretches, the sound takes a fraction of a microsecond longer to return, and from that, you can calculate the actual elongation and therefore the actual tension. Or they use turn-of-nut methods, where you tighten the bolt to a snug condition and then rotate a specified additional fraction of a turn, relying on the known geometry to produce a predictable stretch. Some bolts are designed to break at a specific torque. They have a splined section that shears off when you've reached the target, giving you a built-in mechanical confirmation. Each of these methods is an engineering response to the fundamental uncertainty in the torque-tension relationship, the same uncertainty that comes from friction eating up most of your input. Here's the thing that ties this back to everything we've been talking about all evening. A bolted joint under service loads experiences cyclic torsional and tensile stresses. The bolt sees fluctuating loads every time the structure it's part of flexes, vibrates, or changes temperature. And what happens to metal under cyclic loading? Fatigue. Wöhler's old nemesis. Bolts can and do fail from fatigue, and when they do, it's often at the first engaged thread, the point where the stress concentration is highest, right where the bolt meets the nut. The thread root acts like a tiny notch, a stress razor, exactly the kind of geometric discontinuity that Wöhler's work taught us to worry about, and that the comet disasters burned into aviation's collective memory. So bolt engineers, and yes, that's a real specialization. People dedicate entire careers to fastener engineering. They design thread profiles to minimize stress concentration. They specify thread root radii. They control surface finish. They select materials and heat treatments to push the endurance limit as high as possible. They design bolts to be preloaded to a specific tension so that the fluctuating service loads add only a small variation on top of a large static stretch, keeping the stress range in the bolt below the fatigue threshold. It's a direct application of the SN curve, thinking that August Wöhler pioneered in the 1850s, applied to a part that costs maybe a few cents, but whose failure can bring down a bridge or crash an airplane. And speaking of airplanes, let me circle back one more time to something that connects all of this. Modern aircraft are held together by millions of fasteners. A Boeing 787 has approximately 2.5 million of them. Each one is a torsion problem at installation, a fatigue problem in service, and a materials problem in terms of compatibility between the fastener and the structure. When you're putting titanium fasteners into carbon fiber composite panels, you have to think about galvanic corrosion, about the difference in thermal expansion between the materials, about the bearing stress on the composite layup, about the hole quality because composites don't drill like metal. They can delaminate if you're not careful. Every one of those fastener holes is a stress concentration in a structure that's experiencing torsional, bending, and pressurization loads millions of times over its service life. The engineers who design those joints are standing on a pyramid of knowledge that stretches back through the Comet investigations, through Wöhler's axle tests, through Navier's beam equations, through Euler's mathematical frameworks, all the way back to Archimedes reasoning about levers on the shores of Syracuse. That's the thing about torsion, and really about engineering knowledge in general. It accumulates. Each generation adds a layer. Archimedes understood the lever. Leonardo sketched mechanisms that converted rotation to linear motion. Galileo asked how beams break. Hooke discovered the proportional relationship between force and deformation. Euler gave us the mathematics of elastic curves. Coulomb and Navier formalized how torsion and bending stresses distribute through cross-sections. Wöhler revealed that cyclic loading is a different beast entirely from static loading. The Tay bridge collapse showed what happens when theory doesn't reach practice. The fourth bridge showed what happens when it does. The comet. Disasters taught us that stress concentrations and fatigue can hide in plain sight until they kill people. And the response to each of these lessons, each failure, each breakthrough, became part of the foundation for the next generation of engineers to build upon. You can trace a direct line from Archimedes' lever to the torque wrench in your garage, from Galileo's cantilever beam to the wing spar of a 787, from Wöhler's rotating axle test machine to the fatigue certification of every bolt in a modern jet engine, from the Tay bridge's collapsed iron girders to the professional engineering licensure laws that exist because of the Boston molasses flood, from Saint-Venant's thin-walled torsion theory to the carbon fiber monocoque of a Formula One car. These aren't separate stories. They're one continuous story, one long conversation between humans and the physical world, conducted through mathematics and materials and hard-won experience. And the beautiful thing? The thing I find genuinely comforting when I think about it is that this conversation is still going on. Right now, somewhere, an engineer is running a finite element simulation of torsional stress in a new alloy. Somewhere else, a graduate student is testing a novel composite layup in a torsion rig, carefully plotting data points on a curve that Wöhler would recognize instantly. In a factory, a technician is calibrating a torque wrench, trusting a chain of standards that traces back to fundamental definitions of force and distance. On a construction site, a structural engineer is checking that the bolts in a steel connection are tightened to the right specification, knowing that the building's resistance to wind loads depends on the torsional stiffness of those connections. It's all torsion. It's all the same principle, dressed up in different clothes for different eras and different applications, but always coming back to that fundamental relationship. Force times distance, the tendency of a force to cause rotation, the way materials resist twisting, and what happens when they can't resist anymore. So as you're lying there, maybe feeling your thoughts start to soften around the edges, here's something nice to sit with. Every time you turn a doorknob, you're applying torque through a mechanism that converts your hand's rotation into the linear retraction of a latch bolt. The same conversion principle as a bolt and nut. The same inclined plane wrapped around a cylinder idea. Every time you ride in a car over a bumpy road and the ride feels solid and composed rather than creaky and unsettled, that's because engineers got the torsional rigidity of the body structure right, using principles that flow from Saint-Venant through Lancia, through decades of aerospace knowledge transfer. Every time you fly in an airplane and the wing flexes gently in turbulence without braking, that's aeroelastic tailoring. Composite plies laid at precise angles to manage torsional response, validated by decades of testing that began in a lab at NASA Langley. The world is full of torsion, quietly doing its work, managed by centuries of accumulated understanding. And the people who figured all of this out, Archimedes in his workshop, Galileo with his cantilever thought experiments, Hooke with his springs, Euler scribbling equations by candlelight despite being nearly blind, Wöhler patiently counting millions of loading cycles on his test machine, Benjamin Baker building a bridge that was deliberately over-engineered to prove a point after the Tay disaster, the de Havilland investigators piecing together the comet wreckage to understand what went wrong, the NASA researchers who spent years proving that composite structures could be trusted. All of them were engaged in the same deeply human project. They were trying to understand how the physical world works so they could build things that don't fall down, don't break apart, don't fail the people who depend on them. And that's a pretty good thing to fall asleep thinking about, isn't it? That quiet, persistent, cumulative effort to understand and to build. The idea that every object around you, every structure you trust with your safety, represents the distilled knowledge of thousands of people across hundreds of years, all grappling with the same fundamental questions about force and material and geometry. Torsion is just one thread in that enormous tapestry, but it's a thread that runs through almost everything, from the simplest hand tool to the most advanced aircraft, from a child's spinning top to a satellite's reaction wheel, from the crankshaft of an engine to the double helix of a drill, bit biting into steel. The forces are always there, twisting, turning, winding through the structures of our built world. And the engineers are always there too, quiet and mostly invisible, making sure everything holds together. Tonight, wherever you are, whatever you're resting on, torsion is at work in the frame beneath you, in the fasteners that hold your walls together, in the hinges of your doors. It's been understood, accounted for, managed. You can trust it. You can let your thoughts unwind, let the tension in your own body release, and just rest. The engineers have done their work. The math checks out. The bolts are tight. Everything holds.